In this video, we're going to wrap up our unit on factoring with really no new directions, no new techniques, just a kind of something to keep an eye out for. And the directions factor completely. Eventually they go away. It becomes assumed that if you're factoring something, you want to factor it down to its smallest parts. And that's not always the case. Sometimes, the context makes you want to do something a little bit different. But for now, in Algebra 1, usually it's a matter of when you start factoring, keep factoring until you can't anymore. So we're going to take a look at an example here, and we're going to actually do this problem two ways. The first one I'm going to call the way that is not recommended to try to drive home a point from some earlier videos. And the not recommended way would be to take a look at it and say, all right, well, so I'm recognizing that it's a three-term expression. And one of the things I like to do when I'm factoring three terms is to think I need to find factor pairs of something that add to something. And that's when we use that observation of with a number in front of x squared, the challenge rises and you go after the outer product of 16 and say, I want factor pairs of 16 that add to 8. It's positive 16, so they'll be like signed, whatever we come up with. And when you add like signs together, it's really going to feel a lot like adding. So let's look at our factored pairs of 16. You've got a 1 and a 16, and they make a 17. Even if I tried to get creative with signs, which wouldn't work in this case, it'd be 15. Certainly not 8. 2 and 8, well, one of them is 8. The sum of those is 10, and that's not going to be helpful. And the difference, again, isn't helpful either. That's 6. Our last factor pair is 4 and 4, and they have a sum of 8. So what we decide to do then is we're going to use that observation that the factor pairs of 16 that add to 8 are 4 and 4. And there's two different ways we can do that. And this has been one of these kind of most challenging things. And I'm going to show you both ways in this video, but just as a reminder, so I'll move quickly. So one way we handled that information was we would take a look at the 4 and the 4 and say, since that's going to work for us, that means the way we're going to think about the 8x is as a couple of 4x's. We'll break it up as a 4x and a 4x. And then at that point, we made a 4-term expression so we could factor by grouping. And remember, that was a 2-step process where you look 2 at a time and say a common factor in the 4x squared and the 4x is a 4x. A common factor in the 4x and the 4, my last 2 terms, is a 4. And the all-important thing is that we have a x plus 1 that matches. So as I go through this, this is the first time that we put parentheses on our paper in our work here. And it might lead someone to think that this is factored. But this isn't factored completely. And the reason it's not factored completely is when I read it, actually not factored at all. When I read it, it reads as 4x times x plus 1. So far, so good. We're factoring, we write a multiplication problem. But then this plus comes along, and you realize this entire expression here, its whole structure is not a multiplication problem. So it's not factored. And that's why this factoring by grouping was always a 2-step deal. So you would find the common factor, x plus 1, throw it outside of a set of parentheses, and rewrite that as that factored expression. Now, I want to point out here that this would be a lot of work is done, and you worked hard, and it might be very tempting to circle it, but it's actually not factored completely. And that's why I don't recommend this approach. One, we had to fight through this 4 and go through all this and factor by grouping. And that's a challenge. But the other thing is when you're done that much work and you've gotten everything down to an x to the first power, my radar for factoring, like my awareness for factoring usually starts to fade. But really, if you look closely, the 4x plus 4, that still has a common factor in it. And I don't think to do that late in the game. So the x plus 1 is fine, that's factored, but this 4x plus 4 is equivalent to a 4 times x plus 1. So the fully factored expression from the beginning would have all 3 of those factors, and you might bother to write it like that. Not recommended probably because when you see what is recommended, it's going to look a lot smoother, I think. And what is recommended is, it was loud and clear in some of the earlier videos, always look for GCF first. I don't care whether it's 2 terms, 3 terms, 4 terms, 5 terms that you're looking for, look for a common factor first. If we had done that, look at the remaining factor. First of all, I think it screams, hey, you might still want to factor here. This might not be factored completely. That squared is at least interesting. And when you take it further and you say it's got that squared and then next to the first and a number, that's reminiscent of that pattern and that kind of symmetry we've been finding. And good news, when you're going to factor what's in the parentheses, you don't have a number in front of x squared. So you can think of factor pairs of 1 that add 2. And once you find them, you can throw them into parentheses. Factor pairs of 1 that add to 2 are 1 and 1. So by the time you're done, you have the same answer. But I think that the work on the right looks a lot better than the work on the left. So that's why I always look for GCF first. Great idea. I'll take one more here. And the reason I chose this problem is because I've seen over the years that when students see larger exponents than 2. When students see multiple variables in a problem, the intimidation goes through the roof. So what I want to kind of put into everyone's mind is the method works. And the method is, I don't care how many terms there are, look for a GCF first. And when you're done that, then closely look at the factors that you've created and see if there's the potential for something else. So looking across here, I see in the first term, I see a 2, a 4. I see some X's and some Y's, okay? In the second one, I see a 2. I don't see a 4, because 4 doesn't go into 18. But I see X's and Y's. And in the third term, I see a 2, an X, and a Y. So I think that my common factor then is a 2, an X, and a Y, and I should take those out first. And maybe that's all that you can do. But what happens when you do that is the exponents have come down from 3 to 2, and from 2 to 1. And the multiple variables that they've also kind of, they're no longer a problem because they're all in this factor here. This has become pretty familiar now. This is one, unfortunately, where there is an a in front of x squared. There is a number in front of x squared. We're going to have to deal with that. No way around it. We took the GCF out, but at least it's much more manageable maybe than something with a higher exponent like a 3 or variables like x's and y's. So we'll go back into that routine. We'll look at the outer product of a 2 and a positive 10, and that's a factor pair of positive 20 that adds to a negative 9. We know factor pairs of positive 20 have to match, and I'm going to be looking for a couple of negatives, but let's just look at the number pairs. 1 and 20, I could make a 21 if I added those together, or if I was creative with the signs, I could make a 19 of some kind. That's not working. I need a negative 9. 2 and a 10, that's a factor pair of 20. That again doesn't work for me because I can't make a 9 out of that. 4 and a 5, that's the one. So what I'm going to do then is I'm going to bring the 2xy down, and I'm going to realize this 3-term expression factors as 2 sets of parentheses. And remember what we did with these things if we weren't going to do grouping. In the first example, I showed you how you could rewrite a 3-term as a 4-term. I'm going to talk about the last thing I showed you in our series of videos, where if you know that these 2 numbers are my outer product and my inner product, and I know a premise for a good guess at how to factor this would be to include a 2x and an x. Watch what happens when you put the 2x here, and remember that your outer product or your inner product needs to be 4. If you know that a 2x is going to be here, and that your outer product has to be a 4 or a 5, I don't think there's many choices of what goes here. We usually fill the x in right now, and we could do that, but I wanted to highlight the fact that this is making my outer product of a 4, and look what is left. There's not many choices left. This 2x squared had to get split up, and we are committed to this. We'll put an x there. And this 10 was also something that was, its factors were going to end up here and here, and a 2 is a perfectly fine factor, and 5 is the remaining one. So let's see what happens when we do that. Put the x there, which is the rest of the 2x squared. Put the 5 there, which is the rest of the 10. Our outer product that we intentionally made has also led to an inner product, which we needed to satisfy. And we didn't even try to do it. It's just what happens. It's what happens when you're really aware, and in terms of signs of B minuses. So we have factored completely this trinomial by doing a GCF first, and then by using another approach. So what you get now is you're going to have a handful of practice problems where the idea is you take a look at something, you try to look for a GCF first, you look at whatever you write after you've taken out a GCF, and you start kind of analyzing the factors you've created and think, does that look like something we factored before? And if so, continue the factoring. And at the end, make sure all factors that you found are listed here. You can get really kind of wrapped up in how much work it takes to do this, and you can forget to put the 2xy. And that's why back here, the very first thing I did was wrote the 2xy before I got into that. So they're the suggestions for this last video, and good luck.